Hi guys, I'm live. I think it's math lesson time. I know I'm very diverse in my content on my channel, but I go with the flow and do what feels right to me, and it feels like math lesson time. So hope you enjoyed the guitar lesson I just did. Now it's math lesson time. Okay, how you guys doing? All right. Before I was talking about, I got it right now. It's not even that hard of a thing in math, but I do have it right now. So if you have a line, I I now I now get what I'm talking about. So you can do point. Let's say you know that point, and let's say that point is A, comma B. And there's X is A and Y is B. That's this point. Then this is the x-axis, this is the y-axis. If any point up here, this is a point, if any point up here is on the line, then you have a certain slope that defines along, and you have a point of the line, therefore you have the line that defines the line. But how do you do that? Well, this point is, let's say, x comma y. So this much is x, this much is y. Let's do that. Then you have the slope would be this over this. And this, the rise, used to say rise over run. The rise is y minus b. And then if you take that divided by the run is x minus a. As you can see, this. And that's equal to m, the slope. That's called now you're starting to get the point slope definition of the line. So you can have y minus b equals m x minus a, where m is the slope of the line and ab is a point on the line. Yeah. So that's what I didn't really have straight last time, one thing. One of the many things. No, just kidding. So now, so that there's that. And in calculus, what we do is let's just jump ahead to calculus, since we've already gone to that direction anyhow. Let's say I'm going to start all over because not much to save here. Let's start with another XY graph. Okay. This is X, this is Y. Now in calculus, though, you have curvy things, nonlinear, limits, change. And let's say you have a point here, but you don't have, it's not a line, it's just a tangent point. It's just tangent line on that curve to the curve on that at that point. But you don't get just the same thing every time at every point of the line, because the line keeps changing slope. The instantaneous slope is called the derivative. dy dx equals f prime of x. If this is f of x equals y, the line. And what you do is you take this point. Now that point could be, could be a, comma b, whatever. And then you take a figurative point on the curve that defines the slope, but it changes as you get closer to the point that you're talking about. So if the m equals y prime, instantaneous slope that is, and you have a hypothetical rise, which would be y minus b over run, which is x minus a, right? And that's equal, that is equal to f prime of x. But the thing is, let me get this straight. You have to make y approach b and x approach a. In other words, the slopes have to approach being at the actual point. And so you say that that I think you say something like this. I think you say f prime of x equals the limit as x approaches b and y approaches b and x approaches a. I'm not sure how to define that right now. As x approaches, what do you call that? As this point approaches the point. So I'm going to say, let's call this rise delta y and this run delta x. Let's use that terminology. So basically you have this going on. So you limit as the limit as, oh, I get it. I'm beginning to get this. The limit as this delta approaches 0, because as it gets closer to the actual line, this delta x over delta y is going to approach 0, because it will be equal to the point at some point. So let's call it limit as, let's pick one of them. Let's go as delta x approaches 0 of delta y over delta x. Delta means change in math, physics, and chemistry. Yeah, something like that. As delta x approaches 0 of this is equal to f prime of x. So you take a teeny little delta y over teeny little delta x as it approaches, as this x approaches this, as this approaches 0. I'll do it that way, yeah. And then that becomes the instantaneous slope, which is the derivative f prime of x. So we say if y equals f of x, y prime equals dy dx. D stands for just like a little teeny change in y and a little teeny change in x is dy dx, which equals f prime of x. As this line goes closer and closer to that slope, the slopes you get gets closer to the actual tangent line at that point you're talking about, and that instantaneous slope is the rate of change of the function, which is the first derivative, or f prime of x. That's what I got for you today as far as that goes. Hope you can see that. Hope I did it right. I didn't use a book in my hand right now. I'm not reading this. I'm just flying with it, but I think that's basically it. And then we have, interesting thing, remember we have E equals limit as x approaches 0 of, now what's that supposed to be? Of 1 plus 1 over x. Wait. No, x approaches, no, not 0. Wait, x approaches, x, infinity, not 0, infinity, though 0 is a cool number too. As x approaches infinity of 1 plus 1 over x to the x, yeah. Yes, x, yes. Limit as x approaches infinity of 1 plus 1 over x to the all to the x. That's what E is. And it's approximately 2.718281828, and then a bunch of other numbers. I don't know how to show it right now, but take my word for it, or just know that the derivative dy, the derivative dy, the derivative, if y equals e to the x, turns out that the derivative dy dx equals e to the x. E to the x is a function whose derivative is equal to itself, which is very interesting. I don't know many other functions, if any, that are true for. Let's get that intuitively, and let's do some more work, and then we'll be done with this video. Let's say that we plot e to the x, like on an xy. I'm running out of ink on my pens. I can't even afford food, much less ink on pens, right? LOL. I can't even afford to get pens, and they run out of ink, and I can't replace them because I don't have any money. And that one's running out. That one's got no ink too. I don't know if I can finish this video. I hope we can. So anyway, okay. So e to the x is a curve that looks like this, like that. Oh, it doesn't need it doesn't go like that. Yeah. Okay. That's like y equals e to the x. At any given point, the slope or rate of change of the function is equal to the function. So at x equals minus infinity, the derivative, wait, how do I get this? X equals minus infinity. Oh, no, x not equal to, wait. Y of x equals e to the x. Slope is equal to the function. Okay, got it. Got it. I almost got fooled by myself. At x equals negative infinity, I'll say I got ink. How do you explain that? Miracle? The function is 0, as you can see. Y equals 0. But so is the slope, because a line that's like a line that's horizontal, it has 0 slope. M equals 0. So that's consistent. The function is 0 as x goes to negative infinity, and the slope is 0 at that point. And then as x goes closer to 0 from negative infinity, the slope comes up a little bit, but then again, so does the function. Here it's a little bit and a little bit, little bit. And at the middle, when you get to 1, when you get to x equals 0, then y equals e to the x equals e to the 0 equals 1. So the value of the function is 1, but then the slope of the function is also 1, because that's a 45-degree angle, or pi over 4. And that is rise over run is equal to each other, the same, 1 over 1, let's say, and that's equal to 1, meaning the derivative, the slope is 1, meaning the derivative is 1, and the function is 1 also. So like I said, y equals e to the x, y prime also equals e to the x. And then as x gets bigger and bigger and bigger, y gets bigger, as x approaches infinity, y approaches infinity also. And you know that a slope that getting bigger, closer like this, approaches a vertical line which has infinite slope. M equals infinity, because it's rising infinitely. It's rising a finite amount with no distance, with no run. So it approaches infinite slope, and as the function itself approaches infinity. So we've shown graphically, intuitively, that if y equals e to the x, the derivative of the y prime or dy dx equals e to the x also. So that's good to know. I can't prove that right now, and in fact, I'm not even sure I'd want to if I could. Let's just leave that for later. But it's just true. So let's do something else. Let's introduce the complementary operation to e to the x is logarithm of x. I'm going to call it the natural logarithm because it's base e. Logarithm x is such that logarithm e to the x equals x. The two functions, logarithm undoes exponent. logarithm e to the x equals x, or e to the logarithm of x equals x. E cancels out log, and log cancels out e. So if log e to the x equals x, e to the log x equals x, log and natural logarithm and exponent are inverse operations from each other. That's what the natural logarithm is defined as. Now, let's do this. Y equals e to the x. I want to find the derivative d of the logarithm of x dx. Let's see if I can do that. Well, if y equals e to the x, then dy dx equals e to the x, like I've already shown. Then if y equals e to the x, I have logarithm y equals logarithm e to the x. But logarithm and e cancel each other out, so logarithm y equals x. Okay? And I want logarithm y equals x. And therefore, take e to both sides. Take e of both sides. E to the logarithm y equals e to the x. E and logarithm cancel each other out, so you get y equals e to the x. That's true, but I didn't get anywhere, did I? So if dy dx equals e to the x, let's do it like this. Dy dx equals e to the x. Let's do that. Then let's start from here. So I can do this. This is my own idea here. Dy dx equals e to the x. Therefore, I want y equals logarithm. Okay, here's what I want. Here's what I want to do, guys. I want to say y equals logarithm of x. And I want to know what dy dx is, because that's the derivative of the logarithm of x dx. So y equals logarithm of x. So that's what I have so far. Y equals logarithm x. Take e to both sides. I get e to the y equals e to the logarithm of x. Let's do this. Write this right at least. E to the logarithm of x. And then that get e and logarithm cancel each other out. So I get e to the y equals x. So therefore x equals e to the y. But I want to know dy, I want to know dy dx, don't I? Dy dx, because that's the derivative of the logarithm of x dx. So how do I do that from here? Well, if x equals e to the y, then you know that dx dy equals e to the y, because we know the derivative of the exponent of the exponential function is the exponential function itself. So you have dx equals dx dy equals e to the y. That's what I have there. And if dx dy equals e to the y, and I want dy dx because that's the derivative of logarithm of x dx, then I just invert this. So if dx dy equals e to the y, then dy dx equals 1 over e to the y, because I invert both sides. But e to the y, what's e to the y? Well, right here, we know that y equals logarithm of x. So e to the y equals e to the logarithm of x. But e to the logarithm of x is x, because e and log cancel each other out. So you have e to the y equals x. And if e to the y equals x, then dy dx equals 1 over x. Which means if y equals logarithm of x, dy dx is 1 over x, which means The derivative of the logarithm of x is 1 over x, and I just proved it. I didn't disprove it, I just proved it. So that's a good, cool way I proved. That's my own idea. I never saw that in a book. I just figured that out myself, but that's one way I know that to prove that derivative of logarithm of x equals 1 over x. If this is boring, I'm sorry, but it doesn't make it not true, right? LOL. Hope you guys can see all this. Almost done, almost done, almost done. So there's that. Is that enough? You guys want to hear anything else? Let's see. There's also something called the chain rule. If I have y equals e to the 3x plus 1, let's say. How do I do, what's dy dx? Well, the chain rule says that the derivative, if y equals f of x, f of g of x. In other words, y is equal to a function of a function. This is g. That look like a g? Yes. If y equals f of g of x, then dy dx equals df dx times dg of x dx. This should be f of x, actually. Yeah, the f of x times dg of x dx. So see that? If y equals f of g of x, a function of a function, then dy dx equals df dx, df of x dx, which is the derivative of the main function, times dg of x dx, the derivative of this little function. That's called the chain rule. Chain rule. So the derivative dy dx of e to the 3x plus 1 would be, first of all, the derivative of f of x dx would be this whole function, which is the derivative of e to the 3x plus 1 of, if this is one unit, is just e to that thing. So that would be equal to e to the 3x plus 1. So far, that's f of x dx. But then you take the derivative of this little thing with respect to x. So now the times the derivative of this. The derivative of 3x plus 1 turns out to be 3. Trust me. It's just a simple rule. So that would be times 3. So dy dx, if y equals e to the 3x plus 1 is 3 e to the 3x plus 1 by the chain rule, knowing that the derivative of 3x plus 1 is 3. It's just a simple rule. You want to hear that? And then we'll finally be done. Okay, let's do that. Well, I might as well, because I brought it up. I might as well, for completion's sake. So if I have y equals 4x cubed plus 3x squared plus 2x plus 3. Take this number times this number, and then take the power and subtract 1 from the power. So the derivative of 4x cubed is 3 times 4, which is 12. That's I'm just going to call it y prime here. Y prime, or f prime of x, but I'll just call it y prime. Come on, magic marker. This number times that number, which is 12x squared. You take the x power down 1 from 3 to 2. X squared. This one is 3 times 2 is 6.